Today's video will demonstrate how to assess the quality of several class designs through the encapsulation metric of abstraction. Hello, I'm James Helfrich. The encapsulation metric of abstraction has 4 levels: complete, opaque, porous, and critical. This video will demonstrate how to identify the level of abstraction for a given class design, as well as the implications of that level. There are 3 encapsulation software design metrics. The first is convenience, and this is the quality of the public methods. And we have 5 levels of convenience: seamless, which is most desirable; easy, straightforward, convoluted, and prohibitive. And each of these is a measure of how well the class integrates into the host application. The next level of quality metrics is fidelity, and that's the quality of the attributes in a class design. We have complete, which completely aligns with the POM domain; extraneous, which means we have extra states or extra member variables; partial, which means we do not completely capture the POM domain; and poor. And finally, we have abstraction. And this is the amount the client needs to know about implementation details of a class to use it effectively. And we have 4 levels of abstraction: complete, which is the most desirable; opaque, porous, and critical. So let's see how we can classify real-world examples based on these 4 levels of abstraction. In our first example, we have the C strings. A C string is the default string implementation for the C programming language. A C string is defined as an array of characters terminated by a null character. The programmer can specify the string literal with a double quotes, like quote string literal, and the programmer can specify a string variable by declaring an array of characters and manipulating and inserting the null character. For an example, I have a string literal called const_char star string literal, and then I have an array of 6 characters, of which VAR are the first 3 letters, and I have the null character. What is the level of abstraction of this C string? Now, the string variable is an array of characters. Notice how the programmer needs to manually insert the null character, or the C string will not be well formed. The programmer also needs to make room for the null character in the array declaration, not skip any indices when initializing the string, and recognize that the first index is 0, and not exceed the bounds of the array. If any of these details are not realized by the programmer, then the code will malfunction. And this is an example of critical abstraction. The client must deeply understand the implementation details to effectively use a C string. Okay, let's take a look at another example here. This is C++ standard string. The class diagram for the standard string has 3 member variables: the array, the size used, and the max. And we have the size, empty, append, access, pushback, and C string as the public methods. What's the level of abstraction of the C string? Now, for the most part, the public interfaces do exactly what the client expects. They manipulate strings, and the client does not need to concern himself or herself with how the string is implemented. In fact, they may never do so. However, the problem comes from the last method, the C_str, which gives the client the direct access to the underlying array. This constitutes a huge breach in the castle wall. With the resulting pointer, the client can manipulate the underlying array so that size used member is no longer consistent with the number of characters in the string. This pointer can also allow the client to circumvent all the public methods. The client can even hold on to that pointer, and then, when a string class reallocates the buffer, dereference the pointer and cause the program to crash. This is an example of porous abstraction. Knowledge of implementation details are helpful to the client. Let's take a look at another example, the Java string. Now, the Java string, we have 4 member variables. We have the value, offset, count, and hash. And then we have some public methods: length, find, index, split, replace, and lower. What's the level of abstraction of Java's string class? On the surface, there appears to be nothing about the public interface which reveals the inner workings of the string class. There is, however, one minor chink in the armor. Java version 6 attempts to optimize on the case when a large number of substrings are drawn from a single string. In these cases, the return value of substring returns a new string sharing the values of the original. The only difference is the offset and count variables are now different. Normally, this is great. There's one less buffer to copy. However, when we then assign the results back to the original string, now we have an unnecessarily large buffer. This is an example of opaque. Unimportant implementation details are revealed to the client in non-mainstream scenarios. Our final example is the Python string class, defined by the PyString object. Now, we are never given access to the underlying implementation. We cannot tell whether the underlying data structure is an array of characters, a linked list, or even a hash. We cannot tell whether text is stored as ASCII values, Unicode, or UTF-8. because these implementation details are completely shielded from the client through the provided public interfaces, a case can be made this is complete abstraction. To further strengthen the case that Python string class is complete abstraction, the internal implementation was changed from version 2 to version 3 of Python. In version 2, str was a 1-byte string. In version 3, it was a Unicode 2-byte string. This change occurred without necessitating a widespread overhaul of Python programs. And thus we can make a strong case this is complete abstraction. No implementation details are revealed to the client. This is example 23.1, .2, .3, and .4 in the abstraction chapter of the software design textbook.